Okay. So I have my screen shared now, and I believe everybody can see my screen. Okay, so yeah, so number basis. Okay, so this section, I believe, we are going to look at the main number base systems that we have. That is the decimal, binary, octa, hexadecimal, and then we'll look at how to work with these four number bases, how to perform number system arithmetics. That is how to add, subtract, and perform all those basic operations in number bases. And then you look at number system conversion, how to convert one number base to the other. Okay. But before that, we are going to look at some general concepts and then number bases. And the amazing thing is that this is something that we all know, okay? But let me see, the concepts are formalized into terminologies and others. Okay, let me just put it that way. And it's very important to know them because for the sake of examination, you might know how to work the number base, you might know how to work with the number basis, all right. But then when those terminologies are used, it might confuse you or you might not know what they represent. So I would brush through that very fast so that we're able to get ourselves conversant with it. All right, so when you talk about number basis or number system, it's just a set of values used to represent different quantities. The total number of digits used in a number system is called its base or radix. And this is the first thing we have to know about number bases. Okay. So let's say if a number, let's call a number system A, okay, and the number system A can accommodate, let's say, three different digits or three unique digits. The key word here is the uniqueness of the digits, okay? So let's say we can have, it can accommodate, let's say, B, C, and then let's say D, okay? Then we can say that this particular number system A is to the base 3 or to the radix 3. Okay, so base and radix can be used simultaneously. It all represents the unique number of digits that are represented in that particular number system. So in order to determine which base you are dealing with, you basically determine the unique number of digits that are present in that particular number of system. So the basic number systems that we are going to look at here, as I indicated earlier, is a binary. Okay, so we are going to I'm coming. It's a decimal, which is the basic because that is what we use in our day-to-day lives. Okay, so we have okay, so the decimal, and that's what we use in our day-to-day life. So we are so used to the decimal number system that when we mention the number, we don't even add the radix of the number. So for example, when we say 10, everybody knows that 10 is 10, okay? But actually the 10, 20, 50, and those things as we mentioned are referring to the decimal number system. That's the most commonly used number system. And then for the sake of number-based conversions, we use the decimal as a reference point. So we are going to look at how to convert other number systems to the decimal number system and how to convert the decimal into other number systems. Once you know this, you understand the basics to performing all computations and calculations involving the various number system. So the main number system that you're going to consider here, or the reference point for all our calculations, we are going to use a decimal number system. And when we reach the you would understand what I mean. Okay. So the first is a decimal number system. We are going to look at a binary. Okay. That is the second most important number system we are going to look at here. And then after that, we are going to look at the hexadecimal. And then after the hexadecimal, we are going to look at the octal number system. Okay. Please, a minute. All right, sorry. So let's continue. So I was saying that the decimal number system is our base decimal system we are going to use here. And then the next most important is the binary, the hexadecimal, and then the octal. Okay, so let us look at these four number systems. Please, I'm coming. All right, sorry, please. Just some disturbances. Please, let's continue. So let's move to the next page. Okay, I'll try my best to simplify everything for the sake of examination. And then after that, I'll introduce us to using the calculators to perform some of this. Okay, but first of all, it's very, very vital and important that we understand the concepts. Okay, so some important number systems are the decimal, binary, octal, hexadecimal. And yeah, so let's go to the next page here. So an unsigned number, okay, A, can be represented using n digits in base B. When we are talking about unsigned number systems, we are talking about number systems that accept only positive values only, okay? It's only accept positives and does not accept non-zero digits, okay? So we are only talking about positive numbers here and not negative. So when we are talking about an unsigned number system, we are saying that it can be represented using n digits in base n. Okay, so basically, the position of any the position of the leftmost the position of any digits in that particular number system is -1. Okay, of the previous. Okay, let me just illustrate this. So, for example, if you are given the number if you are given a number 11011 in binary, okay, that is base 2. So the position of this particular number here, that is this one would be what? That would be 0, 1, 2, 3, 4, will be 4, right? So the position of the next number becomes the position of the previous number -1, which is 3 here. So that is 4 minus 1, which is 3. And the position of the next number becomes 3 minus 1, which is 2. The position of the next number is basically, it basically follows that format. And here becomes 1, here becomes 0. So the position of the first digit towards the left is what we always use as our reference point when determining the position of the other digits. So you just look for the rightmost number in that particular number system, and you label that as 0. And the number that comes before that, the position is 1, then 2, then 3, then 4, etc. Okay, so the position of second digit towards the left side of the decimal point is 1, similarly, etc. So please, let us look at this here. That is how to determine the number of representations that a number system can, and a number system with a specific number of digits can accept, and the maximum number of ways that the maximum number that can be accommodated within that particular number system with the given digit. Okay, so let's not look at everything here. It looks a lot for like formula work. Okay, so let us use this general example. Assuming you have a number, let's call this number 525, okay? And this is to the base 10, which is decimal. Let's ask ourselves the question here, how many digits are there within this particular number system? We have 3 digits, right? So we have 1, we have 2, we have 3. So we have a total of 3 digits, okay, within this particular number of system. And then this number of system is 2 the radix 10 or 2 the base 10. So what we are saying here is that if you want to determine the number of representations that are accepted within that particular number, this particular number system, which is this particular decimal number of system with 3 digits, we are going to take the radix, which is 10, and take it to the power, the number of digits here, which is 3. Please, I don't know if you are getting that. So if you want to find the number of representations accepted within a particular number of system with a given number of digits, you basically take the radix, which is the base of the number system, and then you take it to the power, the number of digits that are accepted within that particular number system. So in this particular scenario, we can say that this particular number of system with 3 digits can accept can be represented in 10 raised to the power 3, which is 1,000 different ways, okay? Which is 1,000 different ways. It means we can arrange any number, okay? Any number in, how do you call it? In the decimal number system with 3 digits in it can be arranged in 1,000 different ways. When we are talking about 1,000 different ways, we are talking about starting from 0, 0, 0, okay, to 0, 0, 1, 0, 0, 2, okay, etc. As in being arranged in 1,000 different ways, okay. So again, if you want to find the largest number that can be accommodated within that particular number system with those digits that we specified, for this particular scenario, we are saying that the largest number that can be represented here will be the radix raised to the power the number of digits, okay, which gives us the number of representations. So we can call it the number of representations minus 1, okay. So you take the number of ways that that particular number, okay, or that particular number with a given digits, okay, can be represented, and then you subtract the result. You subtract 1 from that result. So in this particular scenario, we have 10 raised to the power 3, which is 1,000, and then we subtract 1 from the 1,000, which gives us 999. Okay, so here we can basically conclude that the largest number that can be represented in any number in a number system that has the radix 10 and 3 digits within it is 999. Okay, and please, this very, very fit to be examined as objectives. You can be given the digits, okay, you can be told that, okay, so in a particular number system, the radix or the base is 10 and the number of digits in there is 4. Find, let's say, the largest number or the largest representation in that particular number system. And B, find, let's say, let's call it the number of representations that are accepted in that number system. And let's look at how we can solve this kind of problems. Please, I just hope I'm making sense. Please, if we are all together, please kindly give me a thumbs up before we move on, please. Okay. That means you are all cool, sure. So let's move forward. So let's take the first question, and that is, okay. So taking the first question, let's say that we have a number system, okay, that contains, let's say, let's call it 4 bits, or let's say 3 bits, or let's just make this a little bit, let's say it contains 3 bits, or let's say 3 digits. Let me just put it that way so that we are cool with it. So it contains 3 digits. Okay. And then the radix of that particular number system is, let's say, 4. So the 4 is our radix. Okay. So we have a particular number system which is in radix 4 or base 4. And then the total number of digits that can be contained in that particular number of system is 3. Let's find I. So let's find I, the number of representations or the number of values that can be addressed in that particular of number system. So let's call it number of addressable values. Okay. So number of addressable values. And then let's find the maximum number that can be represented in that particular representation. So please, can we all do this independently and then share our answers? I just want to make sure that we are all following. So please, let's do this independently and then share our answers. Please, in case you are done, you can kindly raise your hand.
Hello, Isaac.
Yes.
What is the question? Are you saying we should do something?
Yes. So yeah. I'm saying that, okay, we have, this is a question again. We have a particular number system, okay, and in that number system, we want it to accommodate a total of 3 digits, okay.
Okay.
A total of 3 digits, okay.
Okay.
And then that number system is to the radix 4 or is to the base 4. Let us find I, the number of addressable or the number of possible values that can be addressed within that number system that we've given. And 2, find the maximum representation in that particular number system, or the maximum number that can be represented in the number system. I don't know if you are good with the question. Please let me explain this again. Okay. We are saying that, look, if you have any number system which has, let's say, ABC digits, okay, this number system, you can rearrange, let's say, the digits in the number system in several ways. And each of these arrangements gives you a whole set of numbers, okay? So, for example, if you have a number system with 3 digits and you are told to, and let's say this is in base 10, okay? and you are told to arrange the digits in that particular number system, you know that it can be 001, right? Let's say it has 2 digits. Let's use 2 digits. That would be simple for us. So 2 digits, you know that it can be 0, 0, right? It can be 01, it can be 02, it can be 03, 04, 05, 06, 07, 08, 09. And when we get to 09, we can now come to 10, okay? Then 11, 12, up to 99, okay? So it means that in that particular number system that we are talking about, you can have the number 00 up to the number 99 represented in that particular number system. And if you are to count from 00 to 99, you are going to have what? 100. So we are saying that that particular numbers, digits in that particular number system can be represented in 100 different ways. I don't know if you are cool. Okay. So the number of representations that can be addressed in that particular number system is 100 different ways. And you find, or you know that it is 100 by taking the base of the number system. Okay. The base of the number system is decimal, which is to the base 10. All raised to the power, the number of digits that can be, the number of unique digits that are acceptable in that number system. And in this case, the number of unique digits here are the number of digits, I mean, not unique digits. The number of digits here are 2, okay, which means it can be 0001, but the number of digits cannot be 3. So 10 raised to the power 2 becomes our 100 here. Okay, so that is how you find the number of possible values that can be addressed in a number system. You take the base and then you raise it to the power, the number of digits. Okay, so it is always base power digits, base power digits, base power digits. And then to find the largest number that can be addressed, you take the base raised to the power digits minus 1. Okay, because you are saying that in this particular example here, the number of ways that we can, the number of possible values that can be addressed is 100, right? But if you want to find the largest value, 100 cannot be it, because we said that that number system only has 2 digits within it, and 100 is 3 digits. So it means that will not be possible. So what you do is that you subtract 1. And the reason why we subtract 1 is because of this 00 here.
Reduce your volume. I want you to sit here. Reduce your volume.
The 00 here is what creates a necessitates the subtraction of the 1. Okay, because technically, when we are counting, okay, when we are counting, this 00 here as in creates a false value, which raises the number from 99 to 100. Okay, I don't know if you are getting me. So we need to subtract that 1 from it, which is a false value, in order to return us back to the largest number in there. Okay, look, we can arrange 0001, 02 up to 99. But if we are counting the number of arrangements within this particular set, we will count 00 as 1. I don't know if you are getting me, which will make the last 99 100 instead. So in order for us to know the real largest value, we have to just take the 00 out of it, which is that 1. So we subtract the 1 from it, and then we are going to get the largest value that can be accepted or accommodated within that particular representation. And in this case, that would be 99. I don't know if you are cool with that. So please, let's take an example again. Please, let me just move on. Yes. All right, sorry, let's continue. Okay, so let us move forward. So please, if you are asked anywhere to indicate the largest number, it is always the number of representations minus 1, okay? So the number of representation is the base raised to the power number of digits minus raised to the power the number of digits. And then the largest number, we just subtract 1 from the resulting value, and then we are good to go. Okay. So I'll leave this question here. Just try it yourself. Okay, so let's say we have 3 digits. Let me call that 3 digits. Okay. And then the radix is 5. Okay. If you want to find the set of all possible representation that is addressable, what you are going to do is that you take the base, which is a radix, okay, that is 5. And then you raise it to the power, the number of digits, which is 3. So 5 raised to the power 3, I believe, is 125. If no, 5 raised to the power 3, yeah, should be 125. Okay, so 125. Okay, and then if we are asked to find the largest number that can be addressed or that can be represented in that particular number, we take the answer we had here, which is 125, and then we just subtract 1 from it, so minus 1, and the answer is 124. Okay, so this is the number of representations. So number of rep and this here is the largest number in there. Okay, so now we can move forward. So this is a practical example here, I believe. So we have 4 bits in base 2 is given by, okay, so 4 bits. Let us try solving this without looking at what they have there. So we have 4 bits in base 2. So we said the most important thing is the number of digits. The bits is the same as the number of digits in there. So okay, so we take the base, okay.
Hello, sir.
Does someone want to say something?
Yes, please.
Okay.
Please, so how about you doing it like this? Once the radius is 5, you multiply
Okay.
the radius by the numbers 1 by 1.
Okay, so you are saying that once the radix is 5.
Yeah.
Okay. So let's say the radix is 5. Okay, so you multiply it by the numbers 1 by 1.
Yes, please. How about
Okay,
that one?
in this instance or scenario, we don't know the specific digits that are. This is how the question will look like. 4 bits in you just be told that, oh, in this particular number system it has 4 bits, okay, and then the base or the radix is 2, okay, which is they could alternatively say binary, decimal, whatsoever, but when they say decimal, you know the base is 10. But then you will not be told as in straight off that maybe a number in it is, let's say, 2, let's call this 5, 3, 4, 2. No, you wouldn't be giving any number within it. You would just be giving that particular way straightforward. Or alternatively, they can give you a number. But if they ask you to find a number of representations, okay, if they ask you to find the number of representation and the largest possible number, that could be represented in that particular system there, what you do is that you just ignore all the numbers here. You just only need two things: your digits, okay, your number of digits, 1, and 2, your base or your radix. So you just count the numbers here, which is 1, 2, 3, 4. And then it means this particular number has a total of 4 digits in it. And then the base, which is base 2. So you just take the base, which is 2, and then take it to the power, the number of digits, which is 4. And that gives you 16 as the... So that gives you 16 as the number of possible representations. And if they ask you to find the largest number, you just subtract 1 from 16, which gives you 15. Please, I don't know if please, this is not number-based conversion. Okay, this is just how to find the largest value that can be addressed within a particular number system, and then the possible number of representations acceptable within it. Please, I hope we are cool, or we are still confused.
Thank you so much. Yeah, I'm
Oh,
cool
please,
with it.
Okay, please, if you are still confused, we would explain it over and over again so everybody understands it. So just feel free to indicate that you have a problem in there, and then we can take it again.
Yeah, but this one I'm okay with it.
Okay, so there's second question below. We would solve it by if you are finding the number of representations, we know it is b raised to the power n, where b is our base or our radix. Okay, so b raised to the power n, where b is our base or radix, and that gives us the number of representations. But if you are supposed to find a maximum number that can be represented, let's call that maximum number. We are going to just subtract 1 from the number of representations, which will give us b raised to the power n minus 1. Okay, so to solve this, we know the largest possible number in here will be our base, which is 2. Okay, so 2 raised to the power the number of bits, which is 4. So 2 raised to the power 4 gives us what I believe that's 16. So we have 16 as our number of addressable representations. And then if we are to find the largest value, we just subtract 1 from 16, which is bn minus 1, which is 16 minus 1. And the largest value in there is 15. Very cool. And this literally makes a lot of sense. Okay. Why do I say this literally makes a lot of sense? You have a number which has let's see 4 bits in it, or 4 different numbers. Let's call this 0, 0, 0, 0, and is to the base 2 or is to the radix 2. What this means is that the unique numbers within this are just 2. Okay, and that is binary. So we are just talking about the number of ways that you can arrange ones and zeros within this. Okay, and you would have 16. Okay, if you are to do that practically, you will note that we could have 0001, 0011, 0111, 1111, and then you could have 1011. Just if you pair them up, you would arrive at the same conclusion, which is 16, being a number of ways that can be arranged. And if we want to find the maximum, we just subtract 1 from it, and then we are good to go. Okay, so let's just say everyone is cool with that. Okay, so now let us look at this, okay? And this what we are saying is that every number, okay, we can represent different numbers. Let's say 451 as we have here. And 451 is in decimal, which is to the base 10. Okay. There is something here that we call weight, okay, and the position. So we indicated what position was earlier. So in this particular number system, we have three different numbers with three different positions, right? And each of these numbers at their respective positions have their weights, okay? So the weight of the number 1 here, okay, can be defined as 10 raised to the power 0, which is the, how do you call it, the base or the radix, raised to the power the position of that number. The position of this 1 here is 0. The position of 5 here is 1. And the position of 4 here is 2. When we are numbering from the right to the left, okay. So the base is 10 because this is decimal. So the weight of this 1 here becomes what? 10 to the power the position, okay? So we have the base raised to the power the position, okay? And we call that the weight, okay, of the number. So we take 1 times 10 raised to the power 0, okay? And then we add the resulting value to repeat the same thing here, which is 5 times the base, which is 10, raised to the power the position, which is 1. So to make this convenient, let's put this in a bracket, okay? Plus, then we have 4 times the base, which is 10, raised to the power 2, which is the position right there, okay? So this would give us 4 times 100, right? Plus 5 times 10 plus we have 1 times 10 raised to the power 0, which is 1, okay? And please, can we see what exactly is happening here? We can see that the weights are the last number, which is at the least significant bit. Please, Abi, we are familiar with that terminology. The least significant bit is basically the number with the least weight, which is the rightmost number. And the most significant bit is the number with the biggest weight, which is the leftmost number. Okay, so the leftmost number, we call it MSB, which is most significant bit. And then the rightmost number, we call it LSB, which is the least significant bit in this particular number system. Okay, so you can see that the least significant bit here becomes 1, then it increases to 10, to 100, whatsoever. So 4 times 100 becomes 400. So let's say 400. 5 times 10 becomes 50. And then 1 times 1 becomes 1. Okay. So the resulting answer becomes 400 plus 50 plus 1, which is the same 451, just as in the question, because we are converting a decimal number to a decimal again, which will result in the same result. Okay. So now we have this whole thing here. Okay. And look, you don't need to know what this is. You just need to know what this implies. And what does this imply? We are saying that if basically you have a number, okay, and that number is represented as, let's say, 10110 points, and the number is a decimal number, okay, points. So let's say 0.101. We initially said that you basically number the positions where the last number to your right takes the least position, which is 1, right? No, which is 0, I mean, which is 0. And then this takes 1, this takes 2, this takes 3, and this takes 4, okay? Please, a minute. Okay, I'm sorry. Okay, so let's continue. So we said that this takes 0, this takes to the power 1, this takes to the power 2, this takes to the power 3, this takes to the power 4, okay? And here we have 1, okay? So if we have this, we have a case here. Every other number that comes after our decimal point takes a negative position, okay? So we have -2, we have -3, okay? So technically, to make this very, very easy for us to recall, we can use a number line system, okay? So if we use a number line system, we can say this is the points here, or this line here is 0. And that represents the position of the last number to the left of our decimal point, okay? And the next number there, the position is, we have 1. The next number, we have 2. The next number, we have 3. The next number, we have 4. Anything else that goes to the right takes a negative position, okay? And we have -3, etc., etc. So if we are representing this particular number with regards to its weights, this will look something like this. We would have 1 times, this is binary, so let's say to the base 2. So we can have 1 times 2 raised to the power 4, all plus, then we have 0 times 2 raised to the power 3. Please, if you don't bring your brackets, it's the same thing. You can put this in brackets. It's still the same thing, because according to board math, we still have to work hard multiplications first. Okay, so plus, we have 1 times 2. That is this particular point, which is 2. So 1 times 2 raised to the power 2. Let me just put the 1 here. So we have 1 times 2 raised to the power 2 plus 1 times 2 raised to the power 0 plus, then everything to the right takes a negative power, which is 1 times 2 raised to the power -1 plus 0 times 2 raised to the power -2 plus 1 times 2 raised to the power -3. Okay, so basically that is how this number can be represented, or that is how we represent numbers when you have decimal points attached to it. So this particular number here, which is 65.375, I mean, you have 0 here, you have 1 here. You have you have 0 here, you have 1 here, you have -1, you have -2, and you have -3. Okay. So what this means is that this is to the base 10. So this is going to be 6 times 10 raised to the power what? 1. Okay. Then that's what we have here. Then 5 times 10 raised to the power 0, which is the power here. Then the next one becomes 3 times 10 raised to the power -1, 7 times 10 raised to the power -2, and then we have 5 times 10 raised to the power -3. Please, let us take notice of this. There is no need, or you don't have to bring any decimal points here when you are transitioning between the positive powers to the negative powers. You don't need to bring your decimal point, okay? It is totally unimportant that you say that after you've reached your 0, you are bringing, instead of plus here, you are bringing a point here. No, please, we don't do that. We consider all this as one separate unit. If you punch all this on a calculator, it will return you back to 65.375. The decimal points will automatically be represented. And do you know the reason why? The reason is because 10 raised to the power -1 is the same as 1 over 10, okay? Which in decimal equivalence, I believe, is 0.1. Okay, so you have 10 raised to the power -2. Okay, it's also 1 over 100. 10 raised to the power -3 is also 1 over 1,000. Okay, which are already decimal units. So since this already accounts for the decimal representations, there is no need bringing a decimal point again. Once you do your conversions, this here becomes 0. Once you do your decimal representations, it's going to return you back to your answer. So you have 1 over 10 will be 0.1, 1 over 100 will be 0. I believe 0.1, and 1 over 1,000 will be 0.001. Okay, so once you punch them or compute them together, it returns you back to this. So please, always take note is that you do not bring the point when representing this. You ignore the point here and you just add the values straight away. Okay, because the negative powers have already made room for the decimal values. Negative powers automatically represents the inverse of a number, okay? And an inverse of a number is automatically in decimal, so there is no need to bring 0 points, your 0 points at the first place. So let us move forward with this. So let's take a random example and then we use that example to settle this particular instance or scenario. Okay, so in this particular example, let's say we have something like, let me call that, let me put, let's say 25.37, okay? And then you are asked to, let's say this is in decimal, and then you are required to perform this particular conversion. What happens here is that you know the position of this becomes 0, this becomes 1, this becomes -1, this becomes -2, this becomes -3. No, apart from the 7, there's nothing there. So that is everything here. So the first thing is to just number your positions, okay? And take into notes the number base you are working with or the number system you are working with. So you take the number that is 2 times your base, which is 10, raised to the power, the position of the first digit, which is 1. Then you come and have 5 times 10, then to the power 0, okay, plus, we said we do not repeat decimal point. So plus 3 times 10 raised to the power -1, and then plus 7 times 10, we have raised to the power -2. Now let us perform this computation. 2 times 10 raised to the power 1. 10 raised to the power 1 is 10. So 10 times 2 is automatically 20, right? Plus 10 raised to the power 0 is 1. So 5 times 1 is 5. Plus 3 raised to the power 10 minus 1 is the same as 3 times 0.1, okay? So we have 3 times 0.1. That gives us what? 0.3, okay? So we have 0.3 plus, we have 7 times 10 raised to the power -2, which we know automatically is 7 times 0.01, okay? So we have 7 times 0.01. That gives us 0.07, okay? So we have 0.07. Now, if we add all this together, we are going to get, let me see, 20 plus 5.
That's an excellent idea.
Plus 0.3. So we have 20 plus 5 plus 20 plus 5, I mean, plus 0.3 plus 0.7. And that gives us I think we have a mistake somewhere. Plus 0.07, no, there is no mistake here. That is 25. This is 25, okay. And then 0.3 plus 0.7 becomes 0.37, okay. Which at the first is the 0 is not necessary. So we have 25.37 as your final answer, which returns us back to the same question, since you are converting a decimal to decimal. Okay, so we have an example here. We have the number 542, and then the number 542. We have the positions represented, right? So here we have 0, 1, 2. So the position of the number 5 is 2. Okay. The position of the number 4 is 1. The position of the number 2 is 0. And then the weight of the number 5, since this is to decimal, is times 10 raised to the power 2. The weight of the number 4 is, we know, is times 10 raised to the power 1. So 10 raised to the power 1. The weight of the number 0 is times 10 raised to the power 0. So to find the actual number, we multiply the face value, which is 5, times the weight, which is 10 raised to the power 2. And then we keep on doing that, which is 4 times 10 raised to the power 1 plus 0 times 10 raised to the power 0. And we have this sorted. So you take this as something that you can work out individually. So let's go to so we cannot try our hands on this. Okay. So let's just do one together. Let's do the B. Okay. So the 357.347. We can say this is 0. This is 0. Okay. This is 1. This is 2. This here is -1. This is -2. Okay, so we take, this is decimal, so it's to the base 10. So we have 3 times 10 raised to the power 2 plus, the second one is what? 5 times 10 raised to the power 1 plus, we have 7. So 7 times 10 raised to the power 0. Then we look at the negative values. We have what? 7 times 10 raised to the power -1. And then we have what? 4 times 10 raised to the power -2. So we just point that, and then we have B sorted. So use that method to compute everything there. So we are saying that digital computer represents all kinds of data and information in a binary system. And a binary number system consists of 2 distinct symbols, which is zeros and ones. So only 2 unique numbers, which is 0s and 1. And it is also referred to as the base 2. Each bit in a binary number system can be 0 or 1. Okay. So an n-bit binary number system, which is B, bn minus 1, bn minus 2, b1, b0, can represent 2 raised to the power n different values. You've already explained that's the number of representations. You said is the base raised to the power the different number of digits. So in a binary number system, you know binary is to the base 2, okay? And binary can hold whichever number of digits. So let's say n. Assuming that the binary number that we are given can hold, let's say, 4 digits. Let's say something like 1101 or anything pertaining to this. And then the total number of digits it can hold is, let's say, 4. The total number of representations will become 2 raised to the power 4, which is 16. We've already illustrated that, okay? So call bn minus 1 the most significant bit, and I've already talked about the most significant bit, which is the left most bit, okay? That is the number to the left, or the number with the biggest width. And then B's O is the least significant bit, which is the rightmost bit. Okay, so 2-bit register can represent 4 different values. And we can already see that here. The total number of bits here is 2, right? The total in binary is to the radix 2. And here the total number of bits are 2. So 2 raised to the power 2. And that gives us 4. 3-bit register can represent 8 different values. We know binary is to the base 2. A 3-bit register only has 3 bits. It means it can be, let's say, 110, 001, let's say 111, and then you can pair it in that order. It can only hold 3 different digits within it. So you have 2 raised to the power 3, which is the number of digits it can hold. And that becomes what? 8, which is the number of representations that it can accept. Okay, so at this point, we can look at addition and subtraction of number bases. Wow. Yes, I believe the time is 10:24.
Please, it's
Okay.
9, not 10.
Sure. Sorry. 9:24. Okay. So the next thing that we are going to look at is the number-based arithmetic. That is how to add and subtract number bases. Okay. The interesting thing is that when you look at the slides, it just
Please, so when are we
takes
closing?
basic. I'm closing right now. That's the reason why I'm not even looking at this at the first place. Okay. So I'll just close latest in the next 5 minutes I would close, please. Okay. So basically that takes basic scenarios. So it means that you'd have to look for much more examples and solve on your own. So I'll try to get much more examples of that and put it on the platform so that we solve. But please let us practice how to find the so far from what we've done right now. Let us go and practice how to find the maximum number that can be represented within a particular number system, given a specific number of digits. Okay, and then let us also go and look at how to find the number of different representations. So number of representations. Okay, that can be represented in that number system. And we said to record the formulas, the maximum representation is b raised to the power n everything minus 1. And the number of representation is b raised to the power n. Okay, where b is the radix or the base of the number system, and n is the number of digits that can be contained in it. And then we subtract 1 to get the maximum. And then you also look at what the position is, what your position is, what your weight is in number system. Okay, so position, we've also looked at the weights. And then what again? The position, weights, and then we also looked at the most significant bit and the least significant bit. Okay, we said the most significant bit is the leftmost bit, and the MSB the MSB is the leftmost bit, and the LSB is the rightmost bit. Okay, so that's basically everything that we've done today. So if you do, or if you did understand all this, then I believe that we are all on the same page. So please, our next meeting, we are only going to solve questions only, and that will most probably be on Sunday. Okay. Yeah, so we would only solve questions from section 1 to the first part of section 3. So what we are left to do under section 3 is number-based arithmetic, which is addition, subtraction of number bases, and we also look at number-based conversions. And then we are done with the introduction to number bases, and then we go to section 4 where we build on the knowledge here. Yeah, so thank you very much for your participation. Please, is there any question or any contribution or anything anybody wants to add up? Okay. So if there is any question or anything, then I've brought my session to an end, please. All right, so please we would meet up tomorrow for, I believe, tomorrow, I believe you just want to know something like that. Okay, so bye. Yes, Vida, I want to ask a question.
No, please.
Oh, okay, I saw your hands raised. And I said, okay.
Yeah, it was a mistake.
All right, then I'm ending the session.
Yo, thank you so much. Good night.
You're welcome.